Welcome, students. So now we'll move on to our next architectural implementation, which is variational autoencoder. So if you notice, what we are doing is we are relating each of these terms with the application in manufacturing. So the autoencoder was used for synthetic data generation. So since I explained with the training module itself, by learning the representation, it is able to produce a synthetic data. But these variational autoencoders are much better in generation when compared to autoencoder. So autoencoder can reproduce excellently, but variational autoencoder can show variations in the generated models. So they can produce diverse outputs. So that's the key advantage of the variational autoencoder. So as explained in the slide, you see here. So the outputs of the autoencoder are deterministic in nature. So what it means is that only fixed outputs will be able to be generated because the encoder, latent representation, decoder. There is no variation there. That's the main idea. So limited ability to generate diverse data, as I said. Uh, so uncertainty cannot be modeled. So randomness cannot be produced using this autoencoder. So what we did is, what they did is they proposed an alternate model, which is a variation of this autoencoder. So if you see the image here, this will explain this setup more, more. So as you can see here, the image, it goes to the encoder, then it gets to the decoder. So in between, the setup is same. As you see, encoder, decoder, same block is happening, but in between, as you see, there is a small change here. So architecture is changed in such a way that instead of the plain latent representation, here the latent representations are converted into a latent distribution. So that's the main point which you have to note. In the autoencoder, there will be a latent representation or latent vector, which denotes which numerically denotes the features of the image. Those features are converted into a distribution using this variational autoencoder. So what are those things? I can again give you a high level understanding. So imagine you are having a plain dish, rice. So that is like the latent representation of a autoencoder. It is just rice. You can convert it into rice again. Nothing you can do. But when you convert into distribution, you add some randomness. Imagine something like you are adding some ingredients to the rice. So you add curd, you add chili powder, you add tomato. What happens is that the rice changes accordingly. So it becomes tomato rice, curd rice, or biryani, something like that. So what happens is that instead of a single representation, it becomes a distribution. So as you see here, by using mean and standard deviation, we can convert it into by introducing randomness and using mean and standard deviation, we can convert it into a distribution. So that distribution, when I sample from the distribution, every time I will not be getting the same deterministic output. What happens when I sample randomly each time? The output will be different. So one time it may be a curd rice, next time it may be a tomato rice. So like that, the distribution will be varying. So hence the name variational autoencoder. As you can see from the explanation itself, so randomness is introduced into the output. So what happens is that the generation or the imagination of the model becomes more. So multiple variations of the model can be obtained. For example, if you train the model on the datasets of a cat and a bird, then you can ask the variational autoencoder to create an image of cat with wings, which the variational autoencoder can do better compared to autoencoder, because autoencoder cannot stochastically model these things, but these variational autoencoders are stochastic in nature. The autoencoder is deterministic in nature. So these things you can understand. I hope you can understand. So where it will be, as you can see, the sampling, as I said, this is the process by which the sampling happens. So how the training happens. I will just give a quick overview here. So what happens is that during training, the loss will be propagated. So what's the original image? What's the generated image? What's the variation between them? That is the loss. So the loss will be propagated to the model again. So from that loss, the model will be optimized. So these, as you see here, the applications of this are for handling noisy sensor data, for process variability, for generating realistic images. So for those things, this variational autoencoder can be used. So one issue with these models, autoencoder, variational autoencoder, is that there is a issue called as bottleneck. So because of this, the variability of the output generated is less. So to overcome this, there are even better architecture like GAN and VAE, GAN and diffusion models, which we'll see in the upcoming lecture. So for specific applications, you can use specific models. So we'll see the next models in the upcoming lecture. Thank you.